This is the Empower Podcast, released March 23rd, 2025, episode 691. System Designer lets you try every part with Michael Gielda. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
I'm Michael Gielda. I'm co-founder of Antmicro.
And you're back for the third time on the Amp Hour. Welcome back, Michael.
Thank you. Thank you for having me so many times.
Oh, it's a pleasure to talk to you. And we're going to be talking about all the things Antmicro's been doing and kind of the various open source projects that you and Antmicro are part of. So I'm excited to talk about that stuff. You and I are often, at this time of year, usually, this is going to come out a little bit later, but usually you and I are hanging out at the Zephyr booth at Embedded World, but I didn't make it there this year, and you're headed there in a day or two. So I'm sad I won't see you there.
Yeah, I wish we could see each other there too, but I'm only going for one day this time. My team's there demoing a bunch of things, and indeed we're at the Zephyr booth as well.
Yeah, that's great. Well, let's start right in there with Zephyr stuff. So you and I know each other from the Zephyr project. I think you were just reelected as the marketing chair. Is that right? Congratulations,
yes.
Mr. Chairman.
Thank you.
Doing your work here in the Amp Hour, talking about marketing. So how does Antmicro kind of work with the Zephyr project, and what are some of the new things you've been working on in Zephyr?
Yeah, Zephyr has been pretty central to our story. We've been involved with the project since almost the very beginning, because it makes sense. It structures data. It makes microcontrollers a little bit more like Linux devices. For those of you who don't know, Zephyr is structured around device trees and data-driven flows that allow you to build your binaries and work with your hardware in a structured way, which is kind of a difference from how some other operating systems do it or how people do it in the bare metal world. And because of that, we've always liked Zephyr and started using it many years ago for all of our projects. Whenever we can, of course, afford it. There are clients who want to use different things, but most of the time, if we can have a say, we're going to use Zephyr.
Mm-hmm.
And Zephyr.
Also, we should say that some of the hardware engineers listening right now, they lament the fact that it's more like Linux, but it's actually, as a hardware person kind of coming up the stack, I always think like, man, this is so crappy to learn that stuff. But once you do, you start to kind of you're like, I see it now. Okay. All right.
That is a little bit true. Yeah, of course. So there are some downsides. Definitely Zephyr's, build system and setup is sometimes challenging for people. And we're always trying to make the developer experience better. All kinds of help in that regard is appreciated. But once you cover this initial kind of setup part, it scales really well. It's a really good tool to build actual products that have variants that can be ported across a range of hardware. All these kind of things that really become important as soon as you start rolling out complicated products. And this is what we do. So kind of Zephyr was a great choice for us. It doesn't mean it's a great choice for everybody maybe, but predominantly, if you're really looking to use it for professional purposes, the investment pays off, definitely.
Yeah. How much has Antmicro actually done that migration? Because that's one of the things I always think about is okay, Zephyr is great. I've done some, across chip porting type stuff, but in practice, do you see companies actually doing that? Being all right, well, we're going from vendor A to vendor B because it is in Zephyr.
Well, that does happen. It doesn't happen very often because I think people just prefer to have that option. They don't necessarily like to, jump microcontrollers. If they're comfortable with a certain vendor, they'll probably use them for as long as they can. But at the same time, just having that possibility is important because you don't want to be stuck with a part that's no longer produced or something. We had this in the chip shortage times. Some of us have already forgotten maybe, but
no.
it was real, right? You could suddenly get stuck with a product that you can't make anymore.
Yep. That I feel like that, well, it sounds bad, but that was good for the Zephyr project. A lot of the chip vendors were calling Antmicro and other companies to be like, hey, how do we get in on this? Because we want to be able to not only have this as an option because our customers are asking for it. They're also asking it because new customers were walking in the door and being like, "Hey, I can't get my chips from other vendor. I'd love to switch to you. Can you supply this?" And they're like, "Yes, we can. If only we had the firmware and software, higher level tooling built on top of it."
Yeah, exactly. And I think maybe to illustrate how this is good, we should look at the device tree aspect and the way we use it with Renode and the Zephyr dashboard and so on. So essentially, what we do is we look at the entire ecosystem of hardware supported in Zephyr, and not just Zephyr, by the way. We're also using U-boot and Linux in that way, but concentrating on Zephyr specifically, Zephyr has a really good data set about hundreds of platforms. It's like 800 maybe right now, where all of them are described in one way, and everyone's trying to make sure that this description is correct, up to date, useful, easily parsable. There are tools to process this data, so we can take that data and process it to output Renode simulation files. And so if we have support for specific cores and peripherals that are included in specific SoCs on specific boards, that means that the layout, like how these things are arranged on the system bus, and what's where, which chip has how many UARTs, and so on, all of this information we're getting from Zephyr. And we can just generate that automatically. And assuming we have a model for a specific, let's say, UART or I2C controller, that'll just work. And we can essentially run as many as, I think, 620 platforms in Renode now because of this. And of course, like, we historically knew it was possible to do this, but it wasn't before we tried and we actually built the Renode Zephyr dashboard, where we take Zephyr, we build it across all the targets, we run simulation in a huge, massive CI with like thousands of, because there's like 12 binaries across 800 boards. So it's what, 10,000 different binaries that we built. And then we run all of them in Renode, and actually most of them do run, right? So it's like binary compatible firmware running in simulation. The scale is like impossible without automation. We used to do this by hand. Obviously, we never got anywhere near that number, right? We had like 50 demos and we are super happy. Oh, we have 50 demos, right? Now we have like, I don't know, 5,000 demos more.
Yeah,
So
that's wild. And when you say the binaries there, you mean like those are kind of the test programs, so like the philosophers table or whatever that's called, like the test programs that are running actually on the core, interfacing with peripherals, like actually testing out the capabilities and showing that it's actually cross compiling to all these different targets.
correct. Yeah. So there's like some Rust tests, some AI related stuff, Blinky. Obviously, these are like mainline Zephyr applications because those actually scale across a lot of targets.
Got it. Could you explain so Renode is, I think, something you and I have definitely talked about on the show before, but can you remind people what it is and then how people are using it?
Absolutely. So Renode's a simulator that you can use to develop complex systems. We can do multi-node. We can do communication over interfaces like CAN, Ethernet, wireless. We can of course simulate single nodes too, as a consequence, right? Like if your system has n nodes and n is one, then Renode can do it too. But I think it's most useful when you're building something complicated. And in fact, we've shown this recently. We've had a lot of interest from the space industry. We have a number of customers there, and pretty much all of them have fairly complicated systems because a satellite or some other like space-bound system just has to have like multiple microcontrollers in it. We have customers in automotive, same story. In a
Mm-hmm.
car, you'll find
Yeah,
like
200,
hundreds.
300 micros
Yeah.
in there. It's nuts. Yeah.
So you can do that, and then of course this portability aspect, this scalability aspect, becomes extremely important because you can't just imagine to be doing all of these things by hand.
Yeah, totally. So just to kind of draw a picture from Renode kind of down, Renode is kind of coordinating peripherals and cores and all that other stuff. But then what is actually doing so like you said, the UART, if it's like a known UART, we can simulate that. What is actually doing that like implementation of the simulation there? Is that NSIM? Is that QMU? Is that some other, or is that actually Renode as well?
It is Renode. Yeah, all of this is
It is
Renode.
Renode.
We have
Okay.
both processor models and peripheral models. We sometimes interface with other tools for like physical simulation or similar things. So Renode's absolutely very easy to integrate with other things. But like for the core simulation capabilities, this is just Renode itself.
Okay. So you have your own model of like a Cortex M33, for
for
instance,
example.
and like,
Yes.
yeah, interesting. So then, what it? I guess you probably talked about the last time or one of the times you were on the show, but like, what is this? What is? I guess I've learned more about Zephyr since then too. Uh, what is actually doing that under the hood then? So then that's just like Python code or C or some other language that's just responding to.
Yeah, for the core, it's C. It's a
Okay.
translation library, as you call it. So you take instructions from one architecture, you translate it to another.
Okay.
And traditionally, that's been x86 as the host, right? So, I mean, most people used to only run x86 machines as their hosts, and then you would have to like
Thanks, Apple.
translate, let's say, ARM. But now with Apple, we actually also have the ability to do ARM as host. So it's basically translating from architecture A to architecture B, where those architectures could potentially be the same. But yeah, you're kind of, people have called Renode Docker for embedded, which is not accurate by any means, but it is kind of
Yeah, it kind
nice
of paints a
in capturing
picture,
the
right?
metaphor. Yeah, yeah.
Yeah. Okay. Yeah, it's good for me because it's two things that I have no idea how they work. Uh, uh, that is good. No, I know a little bit about both work. I think. Okay, that's cool. And then when
Same.
people are kind of gluing it all together, like the automotive and the space examples are interesting. So then the so someone's writing high level control software or sorry test software for like a car. They want to like test like user stomps on the brake, and
Yep.
then
What happens then?
it fires system calls throughout the system, and down the line, down over the CAN bus, and it does this and this and this, and it triggers this system and that system, and you like want to see the behaviors that respond as a result.
Yeah, exactly. And you can do it in many ways, of course, but like we believe that definitely simulation where you're running the real binaries is at least one of the ways you should be doing it, right? Because theoretically you could, mock things and model things on a higher level and just, like completely avoid the hardware oriented stuff. But in practice, of course, a complicated hardware system has so many ways to fail that it's kind of better to have that kind of simulation capability in place where in the end you can take the production binaries and run the test, and you're kind of saying, hey, look, I've tested those specific binaries and they do work. And also, like in terms of continuous integration, it's just so nice to be able to, when you're contributing code into a system's firmware, you are testing the same exact binary firmware that you're compiling for your target machine. And maybe you even have hardware in loop testing. You should, right? If you're building a car. And you'll be using those same binaries for like Renode simulation and the hardware loop simulation. I think this is very valuable.
Yeah, I feel like that was always a missing piece for me when I was like starting out with microcontrollers. I'm like, why would this matter? Like, I'll figure it out when I'm on the bench. But it's just when you think about, I think the car is a great level of complexity because it's like if you're working on the, I don't know, the like a window controller, like a up down window controller, and the circuit board for that, and the firmware for that, because there is firmware in there now, I'm sure. And it's like tying up the LIN bus, and somehow like the LIN bus actually triggers something down the line that like the ECU that's interfacing the LIN bus to the CAN bus, and those are all tied together, and like you cause a lockup like way down the line. But if you don't know that until the integration stage, like when you're actually like pushing the down button on your window in the test car, like that's going to throw
That's just
everything
way
into
too late.
chaos.
Yeah,
Yeah,
exactly.
yeah, exactly. So
But
that
yeah,
is
I mean,
good.
the car industry is kind of specific in that,
Sure,
special in
sure.
that
Yeah.
it's both like ancient and complex in some ways. But although it's close to people because everyone drives a car. But I can maybe use the example of the space industry in the sense that there's a sudden boom in space exploration. There's a lot of companies building satellites and so on, and we've been helping people get their stuff to orbit. We have this
Oh, cool.
great customer at Aerospace with whom we've been working kind of in a really rapid development project where, from concept to orbit below 1 year. That was like the headline for it, right? So, and we built
Well, one
everything
year
there.
development and then like 3 years waiting for a launch window or something.
No, no, actually with SpaceX, you can pretty much get your stuff into space. We did have a delay actually. So there was this like little glitch somewhere last summer, but
Mm-hmm.
but it was a delay of 1 month, right? So it isn't so bad these days if you're launching something fairly standard. And so we could build like the whole thing in simulation, and for example, like as in many projects, this one also kind of, there was a change of hardware somewhere at some point,
Mm-hmm.
and the
Mm-hmm.
fact that the things we're using are portable, both Zephyr and Renode, etc. It's like, okay, we're changing hardware now because reasons, but
Mm-hmm.
that's okay because the underlying abstractions are the same.
And so, what was the thing doing?
It's like a data center in space, let's call it. So a processing system that instead of beaming everything to Earth, tries to process data on board. The main computer there is the Jetson Orin, actually. So that was kind of I think maybe a historical first. Getting that to orbit, and of course Athero was doing the work related to making it rat hard and so on. We've been helping them with building the hardware, but they're kind of in charge of making this, space grade.
Yeah, I was gonna say
But
NVIDIA chips aren't exactly. They're kind of big, small.
they're not by default. Yeah, they're
Yeah,
just
right.
kind of
Small
consumer
geometry is
industrial
not great
electronics.
for rays.
Yeah,
Yeah.
yeah. But
Okay.
there's a
But
company called Cosmic Shielding Corporation that's also building those kind of shields for
yeah.
COTS hardware, and
Okay.
that's what they've been using.
Okay. That yeah, I'm sure that helps. They
So
put like
yeah, this has been
water
a great
around it.
project.
That's
Yeah.
my sci-fi brain's like, oh, you could cover it in water. That helps with space rays. But is it something else that actually like you don't want to put lead up there, right? But for
Yeah.
shielding.
Yeah, but anyway, like these kind of projects are really awesome to work on, and there's real challenges, and you can see how simulation just helps tremendously, because you're not going to be able to, you know, test in the real world too much. Um, we have also other customers who have been using Renode in space contexts for, testing, and we've even discussed like training, where a lot of the time, when you want to do training, you need like the full setup lying flat on your desk, and maybe you only have three of those. And every time you have to like get this thing running, you need actual engineers to turn it on and operate it, for people to get trained in how to operate the mission. And the mission operators are not necessarily engineers, right? They might be, but they might be other kinds of people. And you can see how it's kind of almost crazy that in order to like run a training session, you actually have to take engineers out of their like room where they're developing the thing, to actually operate it as well in the testing room, whereas in the training room, right? Whereas with Renode, you could potentially just kind of do all these tests in simulation, and because it's all like automated and scripted, and there isn't like 5 different MCUs you have to flash or something, then you just
Yeah, but
press
how
a
do you
button.
tie together the so this is always the push pull, right? It's like so in that case, I have a very specific like simulation and training versus the reality thing. When I was at Samsung, oh so many years ago, like 2006. So they didn't let us touch the semiconductor processing equipment. They sent us to like a training center and like, it was like using the control software that was not tied to the actual plasma etchers that were there. And so I like sat in a room for a week, just like clicking on a UI interface that was like, oh, and now the wafer has moved into the container, right? And it's like, I don't know if that's actually reality. And like, like that's so it's always that tying of the simulation to the reality. How do you actually validate that piece, right? I mean, like the fact that it actually is doing in the physical world what the simulation's saying.
Yeah, or the other way around, right? Like
Sure.
of
Yeah.
course,
Yeah.
depends
Great.
on the
Yeah.
industry, depends on your
Yeah.
use case. So
Yeah.
definitely, replacing everything with simulation is not possible. But like we're always talking about the Pareto principle, where 80% of the time you probably want to be testing a simulation, and then like once you know what's going on, once everyone's been trained and things are working, you're pretty happy. You should still go and actually like see what the thing does in practice. But you reserve that to really iron out the last details. You don't go, and because like very typically we've seen this over and over again, especially among our space customers, many of them will reach out to us and say, our hardware is not even available yet, or we have 2 copies or something.
Yeah. Right. Right. It's so expensive,
And so
or
like,
it's in space.
yeah, you can't just very simply scale it, right? Like you'll have the barriers of like physical location of the teams, or maybe someone's traveling, and then with Renode they'll just grab a laptop and they'll do work. That's kind of the beauty of it.
What is the level of? I guess so. maybe that satellite's not a good example. If we can just switch back to the car for a second, right? So like the the actual like actuation of a thing, right? So I guess it could be deploying solar cells, right? So like I enter this command, it filters through all the different subsystems that need to do it, and then a a little arm on the satellite deploys a solar cell. So like in Renode, how do you actually? Is it like you're watching a register and it's going from 0 to 1, or is it like there's some other kind of like visualization, like the the thing has happened? Like how does the user know that?
Oh, that's a very good segue, really, because yeah, we've been working on this. Obviously, on some basic level, it's a zero turning to one, right? But then you're thinking, okay, how can we? First of all, how can we like plug this into the external world, so that, or not maybe the physical world, but I mean like a simulated physical reality. And that's one of the aspects we've been working on. Where first of all, we have like a data ingestion format called Renode structured data, Renode sensor data REST, and
Okay.
this REST format allows
Wait,
us
rest?
to
That's
res
confusing.
RESD. Sorry, hard to pronounce.
Aha, okay. Res.
And
Okay.
so basically, you have a file that would kind of specify what data points happen at what points in time. So it's like one time axis and multiple data points potentially. We've been working on this with like some consumer electronics customers, logistics customers, and space customers to, use REST to kind of have like a unified way to input data from the outside into Renode. And then of course the control loop happens in Renode, and then outputs happen. So that's the ingestion part, and I think this is kind of very useful to have standardized because you're not like getting those data points independently, but you can kind of first of all, many customers have some data pools, right? They have specific data recorded maybe, or some synthetic data generator and so on. So we only need to convert it to that format, and we can use whatever
Can
people
we like
have.
make up a fake example? Can we go back to the two examples you're talking about, or make up another example for like what would be in this res RESDF? Is that right? Renode structured data format. So
Renode structured data is sensor data, so
oh, I
just
see. Oh,
RESD without
resd.
the F.
All right.
So
RESD. No.
so let's imagine like a number of data points as like acceleration, maybe temperature and pressure, let's say. Yeah. So we used to build drones. We still do, right? So sometimes we have customers building drones, and you need like, you need to know what the acceleration is. You maybe need to know what the ambient temperature is, and pressure definitely need to know as well. So like you have those parameters, and like all of them are important for a control loop. And you have a file where just the data points are specified. You feed that into Renode, and it just like unfolds this data series, in time. Renode has virtual time, right? So this virtual time kind of is correlated, right? And every time Renode runs is going to be the same like timeline. Like things don't happen randomly. They can if you want them to, right? You can actually change the seed, or you can randomize things by like if you want it. But by default, if you're just going to run the same script, it's going to run the exact same thing, the exact same way also. So yeah, you have
This is
this
a good
data, and
example
then
too because I imagine with like control data for a drone, it's tough to like you can't like tune it in situ. You can't be like, oh well, I'll just modify the PID, the proportional element of the drone's response on rotor one because then it's going to crash. You can't do
absolutely.
that like while it's flying. Maybe you could, but it's tougher. I feel like.
Absolutely, yeah, yeah. So that's one of the things where simulation helps in finding like testing in a wide variety of use cases. Because normally you would test things, of course, like of course people, when they're building products, they're not stupid. They're building those things and testing them in the field. But this testing typically takes like a lot of time. I remember when we were at university, Reno did not yet exist. We're working on these kind of systems. Like 80% of the time was just testing, right? And testing, I mean, like with a drone in your hands, and or like sensors mounting things to walls and things like this. Um, and then obviously you spend a lot of time testing, but you still don't test everything because you can't be bothered to do everything. In simulation, you're like, okay, I'm on a computer. I can just like be creative. I'll come up with a new test scenario, and it only costs me more compute power, which can be parallelized, right? Like you can have 1,000 Renode runs across 1,000 servers. So in practice, you start getting like creative in terms of like what kind of corner tests you're gonna test. You can also do things like accelerate time. So if your system isn't like really busy, if it's not like busy looping on something, which is hard to simulate, but if it's mostly just reading something here and writing something there and maybe sleeping for a while, you can just squeeze that time, and you can take like a week's worth of data and compress that to, let's say, 15 minutes, right? And now you've tested the behavior of a system after a week,
Yeah.
which normally takes a week, right?
Yeah. Right.
And I
After
remember this
using Renode
Boeing
and
problem
accelerating
where,
time, I can tell that this drone will not work at the heat death of the universe. Uh,
well, yeah, maybe that can't be tested easily. But I
yeah.
remember those
Right.
those problems where like something would happen after a year because like a counter would overflow.
Oh yeah, that's a good one. Yep, exactly. 32 bits
Um,
is only so much, huh?
Yeah, so this can be tested in simulation much easier. I'm not saying that, of course, you'll always catch it, because you have to be creative enough to figure out that this could be a problem. But like, if you figured out this could be a problem in real life, you wouldn't be able to test it very easily, because you'd have to like write artificial maybe firmware and tests. Whereas in Renode, you take the production binary and just say, okay, let's see what happens if a year passes, and
Yeah. Yeah.
uh, you know,
That's good. That's good. What about the variety of kind of stimuli, I suppose um, that like how creative can you be there, right? Because it's like the temperature shoots up to 100 C. It's like okay, it's not going to happen, but you could do that. I mean, like that would be like testing like boundary limits on sensor data, I guess, and maybe that
yes,
would cause an
absolutely.
overflow, right?
So of course we can't simulate like physically what's going to happen if 100 degrees happens and your hardware melts, right? This is not going to be something you
Yeah,
can test in
yeah.
Renode. But
Reality's
in
probably
terms of
gonna
the control
smack you in
loop,
the face a different way.
yeah, in terms of the control loop, absolutely, you can do like a borderline criteria that are very difficult to simulate in reality, because you'd have to like heat up things very heavily, and that would break them in different ways. So testing the control loops in border criteria and border conditions, I'd say, is also another great feature
Yeah,
that you
yeah.
get with simulation.
Yeah, and I guess there's like combinatorial like weirdness that could happen too. So it's like at
Yeah.
the sensor one is doing this and sensor two is doing that, and for some reason
Yeah.
those interact. You could have
Yeah.
like, is there like data fuzzing you can do to like kind of cover
We've
a
actually been
wide
doing
variety?
fuzzing, yeah, yeah. Not,
Yeah.
we haven't
Okay.
done as much of it as I'd like yet, but I mean, this is a growing topic,
Yeah.
and I think more people want to do it once they realize that you actually can do it, and they've run out of the simple things to test,
That's right.
and
Yeah.
then
Yeah.
you realize, oh, we could do so much more.
Yeah. Yeah. That's interesting. Yeah. I mean, I imagine like you said with space customers too. Like they only really get one shot, so they need to be really good at that stuff and like having
And when
different
you mentioned
stimuli.
fuzzing, like it reminded me of like the work we're doing right now with automl for this kind of ties for me with our kenning framework. We have like this open source AI framework for, well, portable AI. As you might guess, we're kind of fans of portability and reusability, and we're just demoing it at Embedded World this week, so it's kind of fresh on my brain. And basically,
It's called kenning. You said what does kenning stand for? Like, is that a topic? I don't actually know that term.
it's kind of a poetic expression, means of expression in Icelandic sagas, where you'd have like a metaphorical expression that would typically begin with the same letter for describing something. Like poetically describing a ship to be like the warrior of the waves or something. That would be a
Oh,
kenning.
I used to do that all the time too. Episodes 1 through 255 of the Amp Hour were alliterative titles, so
Yes,
you
so
know
that would be a
I'm
kenning.
I'm quite a kenneringer myself.
Do you have a skateboard, baby? Or no? So no. So basically, Kenning is also using Renode, by the way, for simulating things, and because we can kind of define AI scenarios and run them across a variety of hardware. And this automl feature that we're adding is like trying to figure out the right parameters for your AI workload, right? So it's pretty much kind of associates with my head with this fuzzing problem that you mentioned. Is like you have to test a lot of things to figure out what's best, and with AutoML you kind of do it. And if you have a simulator, you don't have to have hardware to try that out and make it happen.
So in this
So
case, the neural network that's running here though is basically creating the variety of inputs for the like a sensor.
I mean,
What's
I
the
think
AI piece? I guess the better question. AI is used so broadly these days, Michael. It's just it's everywhere. It's it's infecting my brain.
that is true. That is true. It's more about the parameters of the network, really. I mean, you can manipulate the sensor values too, of course, and see what happens. So, like, all of these things become variables. that's that's maybe one of the reasons behind the complexity of the task is you both have like data sets, but also you have like maybe your neural net, for example, which has like, thousands of parameters, sometimes millions, right? Like billions right now, right? So there's so many things to tweak, and you have to have some way to benchmark if you're getting better or worse as you're tweaking those parameters. So
Okay,
so
so
that's
it's
kind
like
of
you're
what
creating
Kenning's
like
in
a
charge of.
feedback into the control system, kind of like
Yep.
the AI control system that is.
Yeah, although it's kind of it's yeah, there's many ways to use this, but yes,
Okay,
in on
I
on a
mean,
high level, yes.
well, maybe we can make it a real test. Actually, it's a board I have on my bench. It's for the Analog Devices Max 32690 EV kit.
Perfect, because this is exactly the kit that we're demoing with. We're actually working on this with
Well, I'm
Analog
looking at
Devices.
your website, so that's that was a
You're
bit
smart.
it was a lead, uh, but okay. So you create a Docker image with the Kenning Zephyr runtime. Mm. So what is the Kenning piece in on this kit, right? So it has the micros that you're targeting and stuff like that, but you're training it to do anomaly detection of something.
Yeah, I mean,
What is?
anomaly detection is basically, can be any data source that's just, supposed to behave in a way, but sometimes, we have
Mm,
weird behaviors, and it. I don't know even what our example is really tracking in
yeah,
terms of like the real variable that's being analyzed, but it doesn't really matter, right? Because it's more about the
right. Well,
maths
it
of it,
matters
right?
only for hardware weenies who don't understand it, like me. That was me. Uh, so like a temperature sensor that might be on board, right? And if it
Yeah,
spikes
or
up to,
a
so you want to like
vibration sensor or something. Like, I
perfect.
think
That's a good
vibrations are
example.
often
Yeah.
used because you can imagine
Yes.
how like something's vibrating at a certain like
Yeah.
frequency, like
Yeah.
something's
Totally.
running as normal, and suddenly, you know, the frequency changes, right? And like,
Yes.
what does
Yeah.
that mean? Maybe something's
Yes.
broken, right? You're trying to detect
Right.
that anomaly.
Yeah,
Right?
and I feel like that's a really good example because writing just like a straight line like threshold detection doesn't usually do the business there unless you're like maybe if you're doing it on an FFT and you're like oh I always know that like the third harmonic is going to spike or something like maybe you do that but like if you want to cover lots of cases and just say normal not normal that's a very good use case because vibration has a lot of data generated and then some kind of weirdness that pops out as a not normal weirdness. That's a good use case. So okay,
Yep. Yep. Yep.
vibration. So I
Yeah.
could.
So anyway, like it's more about finding the right training parameters and like actually building the model for
Mm-hmm.
use on the microcontroller later. Uh,
Okay.
and that process in itself is complicated because
Totally. Oh yeah. Yeah.
if you're gonna like go and tweak everything yourself by hand, you're just gonna be like, okay, whatever. Am I
Yeah.
getting better even? Maybe you are,
Right.
maybe you
Right.
aren't. So
Right.
that's where you're using kind of a feed, kind of control loop in a sense for like the training, and that's basically what AutoML is.
Got it. So AutoML is the thing that's ultimately like the plumbing that's making it easier to build some of these models to like push down into the micro. Is that a good
Yeah. hmm
summary? Okay.
Yeah, and you still need to like actually, assess how it works in the end. So you have to have this like execution control loop, right? But it's more about like executing it enough times that you run into this like optimal solution that you think is good with given your data, right?
Mm-hmm. Mm-hmm.
And then you use that model for a while. And of course, like there are also more topics there, right? Because then you can kind of continue retraining that model to fit better to the actual scenario. But here we're talking more about the moment when you are developing the algorithm in the first place and trying to find the right parameters and tune them to the use case. given a
I have
specific data set.
another example that's from my past that's just a counter example of why to use something like this. It would be like a co-op I did many years ago where I was like trying to detect, it was like, actually on an FFT type of thing, and I was like tweaking an FPGA and I'd generate all the logic and I'd run it all through this different thing, and then like 4 hours later after my computer crunched on it, it'd be like the only thing I had on the output was like again just a 0 or 1, and it'd be like nope, didn't do it, start it again. So I'd get like 2 runs a day, and it was just me clicking a button and then trying stuff in between, but there'd be no like loop cycling. It was always just Chris in the loop clicking
Yes,
go and trying stuff, and like I was a co-op, so I had no
exactly.
idea what I was doing. And so but like being able to actually like model this and run a bunch of scenarios, like it would be better to run 1,000 inputs and get some actual better data on the output, and
Yes,
then feed
yeah,
that back in.
exactly. And that's kind of, I don't want to say it, but like it's eliminating Chris from the loop, right?
Good. I didn't do much at all at that co-op because I mostly just sat around. I mean, like honestly, I could have been doing other things.
Yeah,
So
and also with like those small devices, remember that you have limitations like memory, where maybe some of the models are really cool, but you can't run them anyway. They're just too big. So you have to like, push the boundaries in different directions and see, which kind of model works best given constraints. I think this given constraints element is very interesting because what Kenning does is, you can look at not just one microcontroller. Like right now, we're running this for this one example
hmm
microcontroller, but of course, like there's a lot of microcontrollers in the world, even and on devices, there's a
sure.
lot of them. So you
Yeah.
might imagine that you might formulate your AutoML problem in like, okay, given a family of microcontrollers with different memory sizes and capabilities, let me try to optimize where I'm optimizing across not just like the parameters, the results, but also like I'd like to use the cheapest possible micro, but at the same time, if that was like really cutting my performance in half, or something, then maybe I'm not that interested in kind of over architecting this or over like simplifying this. Maybe I'm okay with using something bigger if it gives me better results. So you can start thinking like more cross-platform, cross like family
Yeah.
in your
Cost benefit
approach to
analysis,
machine
really,
learning.
right? I mean, that's almost what
Yeah.
that is.
And that maybe also brings us to like the system designer concept, right? Where one of the things that we're trying to do very heavily is, try to reason about the world's hardware in a structured, systematic way. There's, so much of it, and it's just hard to pick, and people tend to just gravitate towards whatever they have on their desk and what they like, and that's fine. Like humans are humans. It's good to use stuff that is sits well with you, but at the same time, if you could have some way to like have all of the world's hardware at your reach and the ability to like really pick what's best for your use case, I think that would be very valuable, and that's what we're trying to achieve. um, it's essentially a portal that we're building, which takes the data sources like Zephyr, like Renode and U-boot and other things. We also have like an open source hardware repository, like data set, we can call it, which we constantly develop because we're building hardware, right? One of the things that we do is we build devices, and when you're building devices, you're building hardware. You're essentially putting together hundreds of components, right? And for all of those components, we have open source footprints and Blender models, so that we can first of all use them with KiCad efficiently and in like a structured way. And secondly, we can generate really nice photorealistic visualizations. We've also recently like done like thermal simulations, like EMC simulations and so on, also with open source tools. So we're kind of building out like an open source toolkit for hardware design. You can really do great hardware design these days with open source tools. And we have this open source library that we also like digest as a data source, and you put it all together and get like a Wikipedia of hardware. And that's what we're building.
Okay, so I went in and I clicked on the CH32V003 EVT board,
Mm-hmm.
and now I can go and simulate it in Renode. I
Yep.
can build different things for it because it got ported to Zephyr, which is bonkers. Um, So you kind of show all the things that are built, all the samples that are built for it, all of the things that are on the board. This is probably too simple actually
Yeah,
as a
this is
board.
this one actually
Yeah.
isn't simulated yet. I mean, funnily enough, if you look at if you hover over the board itself, you'll see that the MCU there, you can actually click it, right? There's a hot area, you can click it. That's like a ESP32, which I don't know you've seen. It's been on the news recently, not in a
Yeah, that
good
was a bunch
way.
of
So
yeah, that was a bunch
maybe
of
we pick
silliness
something
though.
else.
Yeah.
Let's grab a. We actually have a board called Environment Sensor. If you could take a look at that one,
Okay.
because I think that showcases some of the things that are maybe
Yeah,
not
sure.
available as assets for other boards.
Yeah. That ESP32 thing was a bit overblown, I think. I knew it when I saw it. I knew it when I saw it. It's not remote execution or anything. Anyways.
Yeah. But so here, if you look at that one, you'll have like a render and a photo side by side, because
Okay.
we have this board, we've built that board, so we have a photo of it, but we have a render, and like they're very hard to tell apart, right?
Oh yeah,
s-
that's
so
cool. Yeah,
on
there's like a
either
little
of
drag
those,
slider that's actually like the overlay of the render over top of the physical you're saying.
yeah, and you can even like the last button on the bottom is to like flip it around,
Uh-huh.
and then you can
Oh
see it's
cool.
the render that turns around, because of course we can't turn the photo around. We're
Mm.
working
Oh, I
on
see.
like the ability to also just have a 3D rotatable board. It's kind of, a bit more difficult because
Like
of
the
the weight.
DigiKey where they take 360 photos and they stitch them together sort of. They don't even stitch them together, they just swap between them.
Yeah, you could do that, but generally speaking, like what interests us is, for example, the fact that we have the whole BOM we've built in KiCad, and all of the components. If you hover over them, you're going to see that they're actually active. You can kind of click on one of them. If you click on the STM32, which we're using there, you're going to see like a specific enclosure. You're going to see that it's an instance of a specific SOC, because this SOC exists in multiple enclosures, right? And if you click add it again, you're gonna go to what this SOC has inside and which boards it's found on and all these kind of things. So there's a
Oh
lot of
cool.
like
Yeah, so we're diving
interconnectedness in
down. It's
there.
got 5 ADCs, 3 CAN, 1 clock, 4
Yeah, yeah,
DACs, 3 DMAs. Okay. And
yeah.
then how are those being used? Like those individual. So it's kind of like you're creating like logical kind of trees of all these peripherals and things like that. But ultimately, what do you do with those?
Yeah, maybe let's go to another board that actually has a simulation demo enabled for it. I just realized that this one doesn't. So maybe go with like some like 96 boards, Aero Core 2. There's also an STM, but this is like just a standard Zephyr target. And this one also has an SoC on it, as you can see, but it also has like all those Zephyr samples, and this time they say passed, right?
Oh yeah, okay, I see. Yep, yep,
And
yep.
when
So
they're
I'm just
passed,
I will link all these things in the show notes for people too if
of
you want to
course,
follow along as you're listening. Sorry about that. This is the Aero board two, Aero Core 2 from S96 boards. Okay, and so we're just looking at this and clicking around on here. Um, yeah, I see. So now we're clicking on. So this is now simulated at the highest level. So Renode is simulating the all of the peripherals that are on the board. So the STM32 talking to what else is on here? Buzzer.
yeah, maybe not all of them, because of course the samples do what they do, right? So Blinky blinks an LED and Hello World prints on a UART, etc. Um, it would be interesting to have like a test that just tries to test everything and just uh, just reacts to whatever is on the board. It's not completely impossible, but of course, like this kind of demo does not really exist in Zephyr, so we're not running it. We could maybe build one. So anyway, point is, these have been executed in our CI. So for all of them, you'll see, if you click on them, you'll see the UART output, and you'll see a trace. Those traces are actually pretty cool. It's like a standard tool that we're using, Speedscope. Um, can you full screen them actually? Maybe not here, but in general, tracing is like something you get for free with Renode, and we're showing this. But of course, like you can also download the assets. There's like a button, and all of these assets are available, and you can run this yourself in a collab, and you can run it, locally. There's many ways you can kind of reproduce those results. They're not like stuck in our portal. This is just a way to visualize them, but this is all like public information and all the binaries. We've heard it from a customer. That was a funny story. We went to customers, and they were like, oh yeah, we're using your binaries to test stuff out, like we're trying to run some Zephyr, on some board, and we were, we didn't want to like compile our own binary. We just grabbed one from your portal and run it, and it worked.
Mm.
So
So how would you imagine? So like, I look at this designer, the designer.antmicro.com, and it has so like the example of this AeroCore 2. How would you expect I would use this in design decisions that I'm making as a hardware designer or a firmware designer, as I moonlight as sometimes?
on a like most basic level, I mean, you can see what's supported in Zephyr, Renode, etc., which is already a nice feature. But more ambitiously, I think what we're looking for is you could click on this board and say, hey, I want to remix that specific board and build something similar, but not quite the same. And we have that capacity generally because we have like this VSD, this designer, system designer. If you click it, there's an actual like diagram editor in there. And this editor contains a lot of the things that are in the portal in general. But of course, like we're still working on making it, good enough for you to be able to seamlessly just click like, hey, let me rework that board and just, change stuff around. And
Okay,
then
so
of
it's
course, like
kind of like a
because
discovery tool. Sounds like for sure. So like I want to be in this ecosystem, so I want to see what's kind of enabled in this ecosystem. That actually is useful. But then ultimately, what is the uh, what is the decision point that you expect someone would make versus maybe building up a board on their bench?
I believe that a lot of the time when we're talking about systems, at least here at Micro, right, we would first start with like, and even when customers approach us, right, they would start with some kind of a high level diagram, essentially. Like they would say, I'd like a board that communicates over this to over CAN and does this and like has those kind of sensors, and they're going to describe it to you in words, and maybe you tell them, hey, words are great, but maybe we should draw a diagram. And the first thing you do typically is you draw a diagram. And we saw this over and over again with people who draw a diagram, and that diagram would be like unstructured, and it would maybe contain errors because someone thinks that a certain device has 4 UARTs and it only has 3, right?
Ah, okay, yeah.
And it's
So yeah, and that's
it's
actually kind of
imprecise.
interesting because
Mhm.
that's often a like a plumbing the data sheet kind of exercise that is non-trivial, right? I mean, like especially if you're doing
Yeah,
it across different families, different vendors, that alone could start to tease out some viable things. Yeah,
correct.
okay.
Yes. So we're trying to automate that process where you're not like drawing on your napkin, you're drawing in a structured system that tells you if you're thinking wrong. And then once you draw this, it becomes a collateral like part of your project where you can verify your assumptions against what you drew in the first place. So you can, maybe even draw an abstract SOC and say, it has this, 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 and this. And then maybe the system tells you, oh, there's like 20 micros that fulfill your requirements here. Mm,
See, now that starts to get into like I always bristle so much when all people approach the amp hour and me and Dave and everyone else, and they're just like, I will design the entire system for you. I'm not saying you're trying to do this, but it's like we have this new AI tool and we'll figure stuff out, and we can design an Arduino from our AI tool. And I'm like, that's not useful. Like the stuff you're talking about, useful, but like the man, I feel like a lot of the tools that are coming into the space right now are solving trivial problems. The stuff you're describing, some of that is non-trivial problems,
yeah.
and so good.
Thank you. Yeah, I mean, I think
The
that's because we're always working with real projects, right? We're always having customers building pretty complicated stuff. We're doing some really nice like augmented reality projects right now, or robotics. They come with like a special set of problems that aren't Arduino level, and and we're not like VC funded where we have to like show proof of concepts all the time for someone to be happy. I mean, we like showing proof of concepts because they're a good way to gather feedback, but like we're not forced to. And what we're really trying to solve is our own problem, right? Renode was created to solve our own problem, and so is system designers. Like, how do you navigate? So we recently came up with this funny feature where we just want to show all the SOCs being used across all of our customer cases. And this is already immense value. Like this is very trivial to do because I mean, we codified. So we use system designer internally, an internal instance to codify the projects that we work on, right? And those projects you typically like say, I have this board with this SoC on it, and I'm running this kind of binary on it, etc. So you have like hardware software components, you're trying to match them, you're trying to build like a complete hardware software BOM of your system. But like even the ability to just show like here's the amount of different microcontrollers and application processors we've been using in all of those projects, you sometimes realize, oh my god, yeah, I didn't remember we did that, right? Like human brain is really weird where after a while you just forget basic facts. And if you don't have a good system that keeps track of all this, and you can just go back in history. So maybe if you go to explore and you take a look at there's like the Axiom camera there. I might have mentioned it in the past. If you go explore Axiom Gamma for Cam, like you can blow it up with the switch view button. It just explodes into a number of boards. And this is like the complexity of stuff that we've built in the past. And you just after a while just forget like what was the sensor used there, like was there like a Xilinx ultrascale board, or maybe it was a Zinc, or did we use a TK1 or a TX1, like. And here you have all of this codified, and so you can kind of go back in time and revisit your past solutions and say, oh, that was actually a nice concept there. Let's maybe reuse this. And it's also a funny way to preserve, like you might be a fan of these kind of things where you know you kind of were excited about some devices that came up in the past that like were released into the market, and 10 years later you can't even like buy them anymore, right? So, and if you wanted to see what's inside, you can't, because you can't see them and nobody had bothered to document them like those 10 years ago. So we're not, of course, like claiming that we're going to be like the Wayback Machine of all hardware, but you could use that in this capacity where, like, for example, documenting the Axiom project, this is in the past for us. This is many years ago, but it was still a useful exercise to do that.
Yeah. This seems like this one's a little bit more complex. Like this is, I feel like one of the push pulls on this is going to be like, I don't have time to document at this level, right? This is so like, I'm sure what you'll say is like, well, if you're starting from the beginning with it, then you build it up over time and
Yep.
you really start to see that sort of benefit. I could see some other benefits though. So like going back to that like UART and like peripherals and things like that, that that is a straight ahead benefit for the smallest of boards that I could see. Does the system designer deal with the kind of the multi assignment problem on chips? So like for example, I use the NRF 9160 a lot. That's a cellular module from Nordic, and it's great. And it talks about how it's got all these different peripherals, in which I'm sure actually I should go to that chip here in a second. I'll go to that SIP. But the one of the problems is that you can only use four. So like you have all of these flexible SPI, I2C, UART, blocks that are in there, but you only get four total. And so like there's that problem that like the firmware only allows it because there's only so many flexible blocks. And then there's also like the kind of multi-pin assignment problem where I might be using UART1 and I want to use I2C2, but I2C2 uses the same pins as UART1. So like how does that get kind of handled?
That is actually a very good question, because Analog Devices has been working on this. They have like a VS Code extension specifically for like pin muxing and these kind of problems. There's other vendors also looking at trying to solve this well, and we're kind of looking to create generic ways to do this. We don't have that featured in the designer itself yet, but I think this is kind of a necessary thing to solve.
Yeah.
So at
That
this
would
point,
be,
no,
yeah, super
but
useful, right? Because then
we're
it's
definitely
like,
looking at it. Yeah, and
yeah,
there
it's true.
are like the stuff that Analog has done is actually open source, so they've been really great in just going all in on like open source, um, which is good, because like as long as it's like a single vendor standard, the problem is that you'd have to support like 20 ways to describe it, and it's just not feasible to maintain this kind of thing. Whereas if it's an open standard, you maybe can afford to figure out like a way to just share, because it's just a thing you have to do. It's not secret sauce really, right? It's kind of a frustrating thing that everyone always uh, um, doesn't like dealing with, but has to. So it would be great if we could just solve it for everyone, right?
Yeah, that would be good. I think another thing would be interesting for me is again like thinking about this kind of tool, having this man, the number of times that a vendor would walk in and they'd be like, "Yeah, I can sell you this great new chip and it solves all your problems needs and you're using STM32 and I'm selling this free scale chip, rest in peace free scale or whatever it is, right?" And then, like and then what they're saying to you though is as the engineer is like, "Hey engineer, I would like to waste your time so that you go and look if this is a possibility." And the engineer just says, "No, I'm not doing that." Like we kind of talked about this at the beginning, like why people don't switch chips in the first place. But if it was literally like if the salesperson walked in and they were very savvy and they had access to system designer, and for some reason you signed an NDA with them as a customer and you said, "Hey, take a look at this system design, see if your chips fit in, give me a better price," like that would actually be a really interesting like use case as well, where now like I as the engineer, I benefit from basically like a marketplace system. I benefit from Zephyr and seeing that yes, actually the code will be ported over to this new system. I see that actually yes, this new chipset that the vendor is pushing me on will cover all my use cases, and maybe even to the point of like you were saying with all these simulations, they even went and ran it for me. Like they ran some like test code on it, and like yeah, it's no problem. Like that would be the ultimate like use case in my mind, where it's like
Mhm.
truly making my life easier as a hardware
Yeah,
engineer.
no, I mean, this is a great idea, of course, and this is, of course, out in the future still, right? Like, I
Oh, of
wish we
course,
could do
yeah,
it
yeah, yeah. I
today,
don't
but
expect it to be, but
well, yeah,
I'm just
that's
dreaming this up as we're talking about it, right? But like these
we
are the
kind of
use
want to get
cases
to
that
a
I see on a
point
daily basis.
where whoever's more open and has better silicon wins, right? Like it's as simple as that. And artificial barriers where people just try to wall people off and make their stuff like as you know weird and niche as possible just doesn't work anymore, and especially with the complexity of the current systems, like they're getting bigger, and you need like more skills to even program an MCU, because maybe it has like a three cores of different architectures, and there's an N accelerator in it, and suddenly you're like struggling with a lot of things at the same time. And obviously, like, everyone's thinking about ways in which this could be simplified, but the worst possible result is everyone comes up with their own way to do it. And then you're still stuck with, okay, as long as I stick with like one vendor, maybe I'm fine. But I don't think that's a good reality. And historically, we've still been reusing solutions as much as we could. Nobody wants to really like jump around and switch microcontrollers all the time, but you do want to be able to just make a pick and just look at the features of the silicon, the price point maybe, but more importantly, just like the ease of use. And the ease of use, I think, should be measured in how much open source software is available for this MCU, right? That's my measure of ease of use. If there's Zephyr, if there's Renode, if there's this, I'm like, I know I'm gonna manage to run my stuff on this. Versus, please download XYZ Studio and like sign 3 NDAs to get this
Yeah,
binary.
yeah, yeah, yeah.
It's like, okay, I don't have time for this.
Yeah. Yeah. Well, and I mean, I think there's some I I'm much closer to the side you're talking about with the, like at least open source in that case is the ultimate backstop of like, okay, I can get at the code. If I need to, I can always go and hire Michael and his team to like help me as well. That sort of thing is really important there too. I feel like vendor support is another like kind of X factor that again, as a hardware engineer in the past, it was always like, well, yeah, we might pay another 20 cents for vendor A over vendor B, but their support team's amazing. And like literally then but like the swappability that we're talking about here, if you could say that and just removes that from the scenario, like okay, now we can just swap over to the whichever vendor is supporting us most, right? Our tooling runs across multi-vendor, and if vendor A is going to help us more, we talk to them more, we give them more business, and it's like this dynamic, it's almost like a pricing power kind of thing where yeah, maybe you're getting them on price, but you're also able to like shift business to them and say more of your chips will make it onto our boards the better supported we are, with manufacturing, with support, all that sort of thing too.
And by the way, these things are related, right? So
Yeah,
if
totally.
you're a vendor and you're really providing good support to people, and typically you're also more open because it's easier to support people well if things are just available and online, and you're not spending your time just sending people binaries over email, right?
Yeah, yeah,
You're
yeah.
writing good documentation, maybe you're organizing webinars to explain things. You're still, it's a lot of work to support customers if you're a silicon company, but I think it gets infinitely easier if you're just more open. And so I think these things go kind of hand in hand a little bit. I mean, I could imagine, of course, a good a vendor that provides open source data but like zero support. That's fine. Like, it would be a very interesting model too. But I think typically what will happen is that the vendor will provide both like more open source collateral and better support, just because even his own team is more productive, right? They're like, they can navigate all of those things easily and point to links, like you can send someone a link, right? And here's the thing.
Hmm.
You don't have to
Yeah,
like
yeah,
say,
yeah, yeah.
please log in with your credentials. I remember we were buying some proprietary tool, and like the amount of time we spent just like getting a license and trying to log in
Oh
to
yeah.
places, and
Right,
it's
right,
it's
right.
just ridiculous.
Is there anything more like defeating as an engineer to be like like, okay, I'm gonna go sign up for this new tool. All right, it's proprietary. I'm fine. I'll get it. Whatever. And you put in your information. You think you're getting a sign up, and then it's like, thank you. We will get back to you in 48 to 72 hours.
Yeah,
What? What? No, that is not how this is supposed to work.
yeah, yeah.
Our
Of course, like
salesperson
I
will come by
wish
your
everything
office and
was.
shake your hand and say hello to you and make sure they get their commission.
Yeah, I think that, yeah, that's maybe one of the problems is there are things that you can just easily buy, and of course, a lot of the new SaaS wave companies and so on, they have a very different approach. Like, you want to buy something, you just click a button, it's there. So it's definitely, there is a good way to sell things that are proprietary and come with like a good user experience and everyone's happy. So I definitely don't want to be like saying it has to be free, otherwise go away. We ourselves
Right,
charge people
right.
for services. So it's not that proprietary stuff is bad or charging money is bad. It's just like, very often, unfortunately, experience is horrible on many fronts. You both pay for it, but also, as you said, you get like mistreated, kind of. And
Yeah, yeah. It's like, oh, you're big, but you're not big enough to get all of our attention. So take the
yeah,
scraps you get, peon. Until
yeah.
Chris is
Well,
at a small company right now. Uh,
so
yeah,
but in any case, we're trying to fix at least some of these problems. We're definitely not going to be able to fix everything, but the good thing is we're working with, for example, right now, this demo with analog devices, right? It's
yeah, yeah, yeah.
They've been
And so
really
you
nice
were
in
helping on
this.
the VS
Hmm?
Code stuff as well, because I
Yep.
had talked to Kevin. Oh, I forget Kevin's last name. Sorry, at Analog.
Kevin Townsend, I
Um,
suppose.
Townsend, yeah, and yeah. So I know he's doing a lot of the Zephyr stuff there. I tried out their tools. It's
Oh
interesting.
yeah, that is
Uh,
their great work. No, no, no. The initial set
oh, I
of
see.
plugins is absolutely them, but we're
Got
working on
it.
the
Oh, cool.
automl plugin with them right now, and
Got it.
of course,
Okay, cool.
like, they're basically doing things that we probably would have done just like they did them, right? Like, I saw the plugins they released last year, and I was really excited. It's good stuff, right? Well designed, nice to look at, nice to use.
Yep.
So we're kind of following that playbook,
Got it.
and the
Cool.
automl plugin will be part of that family.
Got it. Yeah, I feel like having the it has been a big unlock for a lot of the Zephyr tooling. Like when Zephyr when Zephyr was kind of getting started, not started, but like when I started with Zephyr at Goliath, at least it was like a lot of command line only, and now there's just been more and more VS Code plugins that just kind of like broadens the base, opens the tent a little bit more, and makes it kind of more. It's not a pure IDE, right? It's not like a Eclipse IDE that gets delivered to you again as like a .exe that goes in on Windows, which some people expect. But I think it's kind of a good middle ground that makes it a little more accessible.
Yep. No, absolutely. I'm excited for Zephyr, and pretty much everyone is at least asking about Zephyr. Not everyone's
Mm-hmm.
using it yet, but it's definitely out there. And at some point, it'll just, like, the economies of scale just happen, and you have to use Zephyr because other people require it, and you have kind of no choice almost.
Yeah, I think a lot of the vendors kind of following each other as well has been beneficial for, again, as a hardware engineer. It's like I get to see that they all want to put more support in, and I'm happy to see it. And kind of more options that I can switch between is better for me.
Yeah.
Kind of opens up the
And
number of things that
sometimes
I
we
can do.
help them too, right? Like
Yeah,
there's been
yeah,
vendors whom we've kind of brought on to Zephyr, and of course, like ultimately you want them to also build up the capacity internally. But sometimes you need a little push, and that's what we're here for as well.
that's great. Yeah. Um, we did not talk about your chip stuff. You've been doing Chips Alliance stuff. I think the first time you came on, you were talking about Chips Alliance. Very quickly, what is kind of going on in the Chips Alliance world?
Oh, lots of things. So maybe one major thing is Calyptra, a root of trust that's been kind of that's joined Chips Alliance as a project, and that project involves some big guys like Google, Microsoft, AMD, and Nvidia, and we've been helping them to first of all just kind of maintain and develop the core, the RISC-V CPU core in that system. That's kind of at the core of the system, let's say, and then also some other peripheral IO, as well as just like verification and some integration. So generally speaking, Calyptra is this root of trust project that multiple parties have aligned on, and they want to continue developing it so that ultimately everyone can adopt it for their chips that they're gonna sell to them in the data center. And those chips will have like unified security. They will have the same RTL in there, the same software, making sure that the supply chain stays uncompromised, that everything's as advertised. So Calyptra is really, really a huge endeavor in trying to increase the security of servers, prevent like malicious actors and so on. And I think it's very important in these times. And like supply chain security in general is something that we look at from multiple perspectives, also with the system designer, right? So I'm very happy that Calyptra is there, and I'm happy to be involved as well, because it's a multi-party project where you have to collaborate. Like you're forced to collaborate, even though maybe in some other fields those companies are rivals, right? Uh, but for security, they just have to figure out a way to make it uniform, because you're not going to have 100 suppliers, develop 100 different security solutions to be tested across like a number of cloud solution providers. Like the complexity explodes. You have to like unify, you have to standardize, and that's what Chips Alliance is about. Is like you find a common goal in the hardware space, because in software it's much more well known as a problem and much more widespread to, yeah, we're gonna build an open source project to solve everyone's problem. In hardware, it's a little bit less common. Of course, there are standards, right? But very few open implementations of standards. And that's what Chips Alliance is trying to change, is that you don't only get a standard and now go implement your own version of it, and then everything's different anyway, or you have to like really carefully certify everything. But instead, it's like, here's a standard, but also here's an implementation. Just go and use this implementation, and we're going to like pool resources to develop this implementation together, maybe with some different ways to modify it here and there, but like generally speaking 99% of what you're doing is exactly the same. So we can vouch for its security. We can even like do a formal certification process, which you can just piggyback on, right? That's what Calyptra is about.
Okay. Yeah, it's interesting. Yeah, we had guest Laura on the show talking about. It was the first time I'd ever heard of root of trust stuff. So I'm not in the server world, but it did seem like the how are you sure that the server you're talking to is the server you think it is? That is kind of always that feels like that's the core of things, and so it seems like the Calypso project is kind of helping move towards that, like again across multiple vendors, and so that
Correct.
everybody kind of has a common language for understanding which server they're talking to at the time.
Yeah, and as a last kind of comment here is that because everyone's kind of forced to collaborate here, you can also think about unifying workflows and building open source tools that help you be more efficient across companies, not just inside a single company. We can afford, because a single company can always afford to just like purchase one stack from someone and sign all the relevant NDAs and just get going, right? But maybe company two does the same thing, except they're using a different vendor. right? And company 3 is using a mix, and then like it's really hard to collaborate versus like thinking about how to build this into a scalable infrastructure where some of the tools are maybe open source and some of the tools are maybe more standardized so that you can, more easily just make people exchange artifacts and talk about things without having to, fully copy another company's setup top to bottom, right? Which might just be even impossible. So yeah, it's a fun challenge to have, and we're happy to be solving this. And there's a lot of good little open source projects that are kind of coming out of it because we kind of have to solve real problems.
Yeah, that's great. Well, Michael, where can people find out more about you, Antmicro, Chips Alliance, stuff like that?
Yeah, so we've actually built a new site called offering.antmicro.com, and this offering is like an interactive website with different parts of our work, so like hardware, software, AI, cloud, Renode, of course, and FPGA and ASIC stuff. And if you go there, you'll see like a bunch of interactive slides with some cool graphics that you can kind of click around and make things happen to illustrate different problems that we're solving. So there's going to be a slide for Calyptra. There's going to be a slide for our work with Verlater, for example. There's going to be many slides for Renode, actually, some slides for Kenning. So you'll be able to get a feeling for what do these things actually do. And the cool thing is, because they're open source, most of the time you'll just get a link and like, here's the GitHub repo, right? Or here's
that's
a
great.
log note that describes how to run it on your computer. That I think is the nicest part, is that it's kind of a sales pitch, but it's also like a repository of good technologies you can try out for yourself.
This looks like index.js on here, huh? Like the slide software, something like it. No,
Sorry.
The slide software that looks like the slide software is index.js, or no? I've used that for presentations.
Yeah, I think it's originally based on Reveal JS.
Oh, cool. Oh, Reveal. Oh, maybe that's what it is.
Yeah.
Yep.
Mm-hmm.
Yep. Okay, cool. Well, that's great. Yeah, this is
You have a good eye for this. Yeah.
a lot of stuff in here. Wow, this is really cool. Okay, well, definitely offering.antmicro.com. Find Michael online, lots of different places, and yeah, it's thanks for being back. I'm sure we'll have you on a fourth time to talk about all the new things we've done in the meantime. So thanks for being here, Michael.
Thank you so much for having me. Have a good day. Cheers.